Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Oh, buenos días. My name is Jose Blakely. I am a software architect in the SQL Server product group. I've been working in SQL Server for many years now, and I have had the fortune to work in multiple versions of SQL Server, starting from SQL 7.0, SQL 2000, 2005, 8, and 2012. Over the last 3.5 years, I've been working on this version of SQL Server, which is a scale-out version of SQL Server, focusing on data warehousing. The product is called SQL Server Parallel Data Warehouse, PDW. And today I'm going to give a quick overview of some of the architectural aspects of the product. So I'll describe what the system is, some of the fundamentals, and then pick on some elements of the core functionality. A product like this is rich in features, and there are many aspects, but I'm just picking some of the core elements of it.
Is this not confidential, I hope?
Well, we'll clean up the slides later. The fundamentals. So what is Parallel Data Warehouse? This is a scale-out version of SQL Server. The system is defined as a shared nothing architecture, meaning all the data, the volume of data that is managed by the system is partitioned. Every node in the system handles its own partition of the data. There is a component that makes the system appear as a single system, even though it's a cluster of computers. The system is scaled, in terms of scale, the system handles from the tens of terabytes to the hundreds of terabytes, including even into the petabytes, depending on what kind of storage do you provision the system with. In terms of how the system physically appears, it's like a bunch of big data computer racks. Looks like a refrigerator. All the various servers are packed inside those racks. You can buy a system that has a half a rack, from a half a rack full of computers, all the way to 4 racks side by side. I'll be describing how the various systems and the various server functions of the system in a little bit, but in the maximum capacity system, you have about 60 nodes, all right? And that's how the system is structured. It's a standard base. All the hardware that is provisioned inside these systems is a standard, industry standard servers and storage. And the system speaks SQL Server, the SQL language that SQL Server has, which is Transact SQL. In terms of the hardware, customers, different organizations standardize to different kinds of hardware vendors. Some organizations standardize to Dell hardware, some organizations standardize to HP hardware, so we provide versions of Parallel Data Warehouse in each one of those brands of hardware. And our focus is to try to make it as cost-effective as possible. A system of like this is a complex system in that it contains many moving parts, right? It has all kinds of storage, all kinds of servers, network switches, all kinds of software settings to make the system work. And so by doing the work on behalf of the customer in configuring the hardware and the software to make the system scale, we are reducing the total cost of ownership for the customer for this kind of a problem significantly. And so our aim is to provide a very low price per terabyte. That's one of the standard metrics Still, the industry doesn't have really standard metrics for deciding how, how cost-effective the system is. But one of the metrics is the price per terabyte. Another metric that I expect will begin to emerge is cost per server. Trying to position the place that parallel data warehouses plays in the context of the entire enterprise data warehousing solution, you'll see that it's just one of the elements of what goes in an organization. At the bottom, you have the transactional OLTP system dealing with the day-to-day aspects of the system. These are the systems that track every single transaction by a particular industry or customer. So, for example, in banking, it will be the number of transactions people make in their banking, the day-to-day transfers of funds or withdrawals, deposits, things like that. For a retailer, is every single swipe of the barcode reader trying to sell a particular item in a store, right? And so all of those pieces of data, all those transactions are collected and aggregated. Depending on the business scenario, some of this data is handled via stream processing, where people are monitoring events as they come. In other scenarios, data is just collected historically, so that later on, other processes will come and try to analyze and data mine the information to be able to find trends in the way the business is moving, and then figure out ways to position the product, or perhaps create different ways to move the business for a customer. So parallel data warehouse is positioned right here. And then from all this historical data, there are additional processing where different departments, different organizations in a business try to aggregate the data, perhaps in the form of cubes, doing some further analytics, trying to do reporting, and then ultimately at the top, the people who are driving the business, managing the business, make hopefully wise decisions on how to move their business forward based on data that comes from the real from the real behavior of the system. So moving to the hardware, this is a high-level picture of the simplest of the PW systems that one could build. These orange boxes over here are meant to define the boundaries of a rack of computers. So at the front of the system, there is what we call the control rack. And the control rack has the control nodes, which are the entry point into the system. These are the nodes. They have a version of SQL Server running right here, but this is the place where data access drivers like ODBC, JDBC, connecting to the system, applications connecting to the systems via these nodes. And it is from here that all the statements are distributed to all the components of the system, okay? So in that control node, there are also what we call the management nodes. This is a place where the appliance, the system, connects to the data center monitoring. Today, in the data center, there are standard tools that help the people who manage the data center monitor the health and the state of a system. And so this will be the place where all those tools get hooked to. The landing zone is for data loading. In a data warehouse, it is common to load large amounts of data every day, from the hundreds of gigabytes to the few terabytes. And so this will be the place where the data loading, the ETL tools will hook up into the system, and then from here all the data will be distributed to the final place. And then there is another set of nodes for backup and restore. Again, data centers tend to standardize to standard backup restore capabilities, and so this will be the place where they will hook up to their backup restore. Now in this rack, this is called the compute rack. This is where the action happens. all these servers also have a version of SQL Server running in them, and every compute node has a partition of data. It has its own collection of storage that it handles, right? And so, this compute node will access the data stored here in this array of disks, and so on, right? Now, we use, in the current version, SAN technology, because all the data in here is organized in RAID 1 format, so that the system can tolerate disk failures or controller failures or any component of the storage subsystem failures, and be able to continue to work. The network of communication between the storage and the compute nodes is via fiber channel, all right? There is another network that is used to connect all these nodes. It's a higher bandwidth InfiniBand network, and here's where all the data movement happens. Sometimes when, for example, in the process, in trying to compute a join between two tables, where the tables are not aligned on the joining column, it's necessary to move one of the tables and redistribute one of the tables so that joins can be performed in a localized, collocated way. And so all the data movement for that operation will happen over this network. All right? There is a spare compute node for fault tolerance. If any of these nodes fails, this guy takes over, hooks up to the storage partition corresponding to the failing node, and then the system continues to work. Question? Sure.
Because you said shared nothing initially, but maybe let's say the storage area network, it sounds like any node can access data anywhere else.
Right. The question is, I said that this is a system that is shared nothing, and yet I have a picture that shows that every storage node and every compute node is connected, which would seem to suggest that every compute node could potentially access any of the pieces of storage here. While that is true, that is not the way we have it configured. So we use every single compute node has its own partition of data in its corresponding storage node. Under no circumstance will this compute node ever try to access data over here. All right. The only reason we call it we use SAN technology here is just for fault tolerance, so that every single partition of data is duplicated here in its own collection of storage arrays. And the only reason that we have this cross communication here is so that this compute spare node can take over any of these connections. That's all. Okay. All right, so this is the hardware. In terms of the software components, again, we have the control rack and the data rack. So starting from the data rack, every compute node has Windows Server and SQL Server running on it. And actually, every compute node here doesn't even know that it is working on a cluster of computers. The system receives requests and processes the queries, returns results. It's really the control node over here that aggregates and coordinates and makes data looks like coming out of a system, of a single system of nodes that are collaborating for a common task. So in addition to SQL Server, we have two components in every compute node. One is a process called the Data Movement Service, DBMS. And then, so basically, this component is talking to every other DBMS and to the data movement server manager running on the control node. And so all the data movement operations are coordinated via those components. And I'm going to talk about the DBMS component later on. There is also an agent, the PW agent. This is a service that is running here for instrumentation. It's looking at all the events, hardware and software events of the system, and is collecting them and aggregating them so that they are actually put together in a coherent form so that the administrators of the system can see what's going on. If the system is healthy, right? If all the storage is working properly, if all the network is running properly, properly if all the software components are functioning well. In the case of a query, it can actually track at what step in the query processing execution the query is. And so the system, basically, it collects all the hardware and software events of the system, aggregates them, and enables the administrator of the system know what's going on with the cluster. So that's the compute nodes. The control nodes have the PW engine. This is sort of like the master system that provides a single system view of the whole component. Here's where statements are processed, compiled, and optimized. Here's where all the orchestration of the subtasks that are needed to process every statement happens. It's almost like a workflow engine. Okay. I mentioned we have a DMS manager, and we also have the PW agent. So I'm going to be drilling down into what goes on here in a few other slides. So, and again, here's where the client interfaces connect to, and we have the entire array of connectivity tools from ODBC, OLEDB, ADO.NET, and JDBC are sort of like providing connectivity to the system. There are ETL interfaces for the landing zone, and here we have a utility called the bulk data loader, which is the thing that enables fast loads into the system. We will have it drill down into this later on. And then we have in the management node an Active Directory. There is a local network in here in this cluster, and the Active Directory manages all the permissions of the system, so that all the activities that go on within the appliance across the various services is done in a secure way. So let's talk about the shell database and query processing. So this is a distributed system, and the system is organized in layers. At the top, in the control node, we have the PW engine, which has several components. It has components for compilation, for management of global metadata. This is collects all the data of the system, all the metadata of the system, the tables that are being created, databases that are being created, all the indices, right? And then it manages the distributed execution, coordination of all the tasks on behalf of a statement. On the control node, there is an instance of SQL Server. It's called the shell database, and that is the instance that maintains all the metadata of the system. Every time one creates a database, creates a table, an index, there is an entry of those objects storing metadata here in the control node. And this instance of SQL Server is used to, again, for managing the catalogs, for compilation and authorization of all the statements. It's in this metadata where all the also all the users are stored, all the permissions, the entire structure of permissions is stored. And so when a statement is compiled over here, we know if the user is authorized to be able to emit that kind of a statement. From compilation, the output of compilation is a collection of tasks, okay? And these tasks are going to be executed across all the nodes. The compute nodes also have a version of SQL Server running, and here's where the user data is stored. The real rows and the customer rows, the inventory rows. Tasks are sent to the compute nodes. They execute their statements and return results. And all the communication between this component, the PW engine, and the compute nodes is performed via the data movement service. All right? So the data movement service contains a collection of abstractions that norm the kinds of communications that can exist between the compute nodes and the control node. In terms of database design, the system handles the standard create table statements of any SQL system, but it has a specific way to determine how the data is laid out across the shared nothing system. There are two manners in which a table can be defined across the system. We have distributed tables and we have replicated tables. These extensions to the DDL create table statement determine the manner in which a particular table is going to be stored in the system. Large fact tables, these are the tables that contain the usually what push the requirement of a scale-out data warehousing system, are usually distributed on some column of the table. So here the customer table is hash distributed on the customer key, which is a column right here. Right? So as rows are inserted into the system determines the node in which the row is going to be placed. All right? And then smaller tables, like the nation table, they are replicated across all the nodes. One of the advantages of replicating tables across the nodes in a distributed system is that you, for certain scenarios, you maximize locality of query computation, right? It's much better to be able to do joins where all the rows are co-located in a compute node, so you don't have to be moving rows across the system unnecessarily. Maximizing the amount of locality of computation in a distributed system is the key to scalability.
So you said replicate across all nodes. Can I control it at a few nodes or some nodes?
No. Usually when in the current system, when a table is denoted as replicated, it goes across all the nodes.
And hash is system provided hash on the hashing.
Right. The system provides the hashing function for this. And this is just syntactic sugar for really, this is not a function that the user gets to write. This is syntactic sugar for a built-in hash function that the system manages.
Hash buckets is also a control.
Right. So the question is, the number of hash buckets is under the control of the system. Yes, because as I mentioned at the beginning, the size of an appliance can be from a half rack full of nodes, which is 4 to 5 nodes, all the way to 60 nodes. And so the system needs to know what is the size of an appliance to determine what kind of hash function to apply. And then there are varieties. Currently, in the current system, we basically tend to hash to the maximum size of the appliance by default. But there are scenarios where you might want to control the span of distribution, right, to a subset of the nodes in the appliance. And so those are flavors. We currently support that, but we know that we need to go there in subsequent releases.
So you can add nodes later on?
You can add nodes later on. But then we have an automatic way. That's why we control the hash function. Because when you add nodes or when you add racks, you can then recalibrate the hash function and be able to redistribute the data automatically on behalf of the customer. But also, I mean, in addition, these hash functions are really interesting pieces because, for example, when you are hashing on a text column or a character column and you have collations of different languages, then you have to be careful about the manner in which you compute the hash function, all right? And so it is very beneficial for the system to control what that hash function does, okay? Because if you start losing rows, then that's a problem. All right, so here's the process of a DDL statement. So a DDL, like create table, enters the system through the engine service, the PDW engine. The table is created in the shell. It's an empty table, just for metadata purposes. The system returns with saying, hey, this table is, you can create, you have permissions, you can create it, an entry is there. And now, that statement has to be propagated across all the nodes of the system. So that task then happens, right? And of course, this is a bunch of statements, all of which have to transactionally complete. And so the system takes care of all these tasks happening, right, like as a unit. So then when all the tasks complete, the statement returns to the user saying your table has been created. So as you can see, in the process of entering this database over here for managing metadata and then executing the created statement, there is a whole bunch of activities touching multiple SQL servers. So the system needs to make sure that a transaction scope happens, that the logs for the system are managed, and so if for some reason one of these operations fails, the system needs to be able to undo the operation. And so we have a rollback manager component that keeps track of all the things that need to happen in each one of these compute nodes, and when something goes wrong, then it maintains the bookkeeping and decides, okay, I need to go and clean up all the stuff that I did, all the partial results that I created, so that I leave the system in a clean state. So this is for query processing. The high-level view, client sends a statement, connects to the system as in the normal way, as if it were connecting to a SQL Server SMP system. The control node handles the compilation of the query and performs the distributed global generation of the plan. Then the plans are sent, every single task of a plan is sent to the compute nodes. Eventually, some statements require data movement, so the data movement service does the data movement, and then the query is executed and the results are returned. Query optimization is a standard interesting task in database systems. The query optimization phase in PDW happens as follows. You start with a statement, select the count of this join, right, of customers and suppliers, grouped by some supplier key. And first the statement gets sent to the shell database where there is a first level of optimization that happens. There is algebraic query simplification, unnecessary column reduction, predicate pushdowns, unnestings, nested subqueries, all kinds of algebraic operations happen at that point. Then a set of plans is generated in SQL Server. Since it's a cost-based query optimizer, there are groups of alternatives that are generated. So we tap into that intermediate state of the SQL Server query optimizer, and we extract all those intermediate plans from the shell into something that we call a memo structure. So we extract all the plans. This is a capability that originally existed in SQL Server for test purposes, so that the test team could actually test that the plans that the query optimizer generates are correct. So in case of PDW, we take that intermediate state, all right, and then we extract it, right, and we look now at we take those plans as the first step of alternatives for the distributed query optimization. But right there, we can see sometimes that some of the statements are redundant, and so we can simplify them, right? We then look at interesting properties. Given the global metadata that we have available in the control node, we know, for example, what tables are collocated or what tables are replicated. So we look at the interesting properties, distributed properties of the tables involved in the query, and based on that, we inject data movement operations, okay, like shuffle or broadcast and so on and so forth, right? And then based on those data movement operations, which are also algebraic operations, we then generate a new set of plans and we cost them, right? And so out of that strategy, we have a whole bunch of costs, right? And then we try to pick the one that is cheapest, right? Taking into consideration primarily data movement operations. In traditional, it's interesting that when you are query optimizing a query that is going to run on a single node, there is the standard heuristic that says try to push predicates as close as possible to the data as you can. And cost-based query optimizers don't even cost that. They just assume that is always going to be a winning strategy. in the case of a distributed system and the way that we have layered the system, entire queries that can execute in a single compute node tend to be very cheap relative to the tasks that require data movement. So the focus of distributed query optimization is on minimizing the cost of data movement. And then the pushing of local joins and local queries to every compute node are considered as what used to be chargeable predicates. You know, they are considered cheap. And that tends to work for us. So once we pick the plan, we generate a set of steps. And these steps include the creation of some temp tables to store temporary results, execute shuffle operations that actually, as part of the shuffle operations, the data movement operations are very rich operations because they don't just move rows around, they actually execute predicates on every compute node, and then they shuffle the results, all right? So, so for example, in this case, we are taking the orders and then doing something on them and then shuffle them and storing them into temp table 1. We are doing the same over here. I guess the assumption in this particular example is that none of the tables are aligned with respect to the join query, so you need to shuffle both. And then the final results aggregated in the control node, and then there is cleanup operations to get rid of all the temporary tables, staging tables that were created as part of the execution of this plan. In terms of statistics, every local compute node manages its statistics. It's a SQL Server. It's business as usual. That is a standard auto stats computed in the user tables like it normally happens in SQL Server. We also compute our statistics on the temp tables that are created by DBMS so that we, when there are operations that involve those temp tables, we can actually do reasonable query optimization. At the global level, in the Shell database, we have the global view of statistics of the system. We aggregate all the statistics from the compute nodes and present a single system view of statistics in the control node. And that's what's used when we do distributed query optimization in the control node. But these statistics currently are manual. They are not computed automatically because the cost of aggregating on this can be significant. So we try to be conservative and manually trigger the generation of those global statistics. Yeah.
When you built the system, you said you could have this test facility to extract the plan and the costs. Do you send several alternatives to each node? Say, if I did this, give me the plan. If I did this, give me the plan. And then you can...
No. Basically, it's just one. And what happens is that the subtree of operations that is represents what you would send to every compute node is just turned into a statement that is sent to each of the compute nodes. Each of the compute nodes is a SQL Server itself. That statement is optimized there again, locally, for the kind of, you can imagine that across compute nodes, tables may be distributed differently, the statistics may be different, so you may have different plans executing in every compute node, right? And so the system, every local SQL Server database will try to do its best in executing that query for the portion of the data that each of the control nodes, each of the compute nodes controls. Make sense? Yeah, because I mean, imagine if you sent that information to every one of the compute nodes and every one of the compute nodes returned to you with a different plan. Now what are you supposed to do? You have to manage all of that at the global level, which is just complexity you don't need at that level. So the general, I mean, obviously, as you know, query optimization is a very rich area, and there are all kinds of twists and all kinds of things that you could explore, right? What we have done here is sort of like a practical compromise. The high level, the first level distributed system optimizes the distributed tasks, optimizes data movement, and then it delegates the local optimization of the sub-statements to the compute nodes, right? And that tends to work really well for us. What happened? How do stored procedures get processed? That's a very interesting question. Let's take it offline because it's very elaborate. Stored procedures are supported in PEW, but they are managed in the control node, and they are like an interpreter that goes statement by statement. All right, so the PEW engine at the control node manages the execution of every single statement. We don't try to parallelize procedural logic because that's a complex problem to try to tackle. So we basically just go for the simple approach, which is we process every single statement one at a time, and if every single statement can potentially be executed in parallel, it does so, right? But we don't try to launch multiple statements and then try to collect results. All right? Just a simple graph taking a 3 terabyte TPCH performance just to show how the distributed query optimizer can improve the performance significantly for certain queries. The very first version of PEW that went out didn't have a cost-based query optimizer for the distributed task. It did have the cost-based optimized queries for the local compute nodes because it's SQL Server running on every compute node. But the distributed tasks were not cost-based. So they were based on some sort of a heuristic that we use, right? And this graph shows the improvements that we got from adding the distributed cost-based optimization phase. In some case we got, so this,
Put out at this logarithmic scale.
this is a logarithmic scale, and then this is the number of times performance the improvement, and so for some queries it's actually pretty good. All right, so obviously this is not an official TPCH. This is just a data point. In data movement, here are the primitives for the data movement service. Right, we have a small set of operators. Shuffle move is a many-to-many shuffle. You take a table and then redistribute it across all the nodes using some sort of a hash key. Broadcast move takes a distributed table, a partition table, or a set of rows, and then just makes a copy across all the rest of the compute nodes. Partition move is like a local global aggregation. Takes aggregations from the end nodes and moves them up to the compute node. The shuffle load is used for loads. In the loader operation, as data is coming into the system, it sends the data to the right place. And then there is a similar set of data movement operations for replicated tables. And it's amazing that the entire suite of SQL can be processed using this small set of primitives. So this is more detail. The DBMS system basically establishes a many-to-many network of connections in the system, and then it is organized as a producer-consumer type of a system, right? That is, every instance of DMS is reading data. It has a number of threads reading data from the instance of SQL Server it handles. And then, depending on the operation being performed, it has to shuffle or redistribute the data to all the n-1 compute nodes, right? And so it basically takes the rows, computes a hash, decides, it's building sort of like network packets, decides in what network packet a particular row belongs, packs those packets, and then sends them, which is what happens over here. All right? And so all these threads are reading data and sending them to all the other n-1 nodes in the system. And then on the other side, the reader is taking network packets. Again, it's a producer-consumer type of system structure. It reads the packets coming from the network, and then it starts deciding where the rows really belong. So that's the basic structure of that. Bulk loading, an interesting scenario for a data warehouse. So again, we have the familiar compute nodes and control nodes, and then there is the landing zone. All the loads happen through the landing zone. And the key participant in data loads is the DW loader utility. All right. So this is the guy that controls all the data loads. Loads are performed in 3 steps. In the first step, a file is created in the landing zone, and then the DBMS core reads groups of rows without worrying about the final destination of the system. Just tries to build packets of rows, and in a round-robin fashion, sends them across all the compute nodes of the system. So this system is just taking blocks of rows and sending them, trying to distribute it where all those blocks of rows are sent across the system. As those rows are received by each one of the DBMS systems over here, then it computes the hash function where the final row where the row will finally needs to live. Some of the rows will, by luck, belong in the node that receives them. Some of them need to be sent somewhere else. So this guy decides where to send them, right? And then there is a staging table here because some of the target tables where you want to load data may have an index associated with it. So in order to reduce the fragmentation of the disk, we create a staging table so that the rows are organized according to the final organization that the rows are going to have in the final table. So if the rows need to be sorted, they need to be organized or partitioned in a particular way, that staging table will make sure that it starts lining up the rows the way they are supposed to be in their final place. And in the end, what we do is an insert select operation, which just simply moves the rows from the staging table to the final table in the database. These staging tables eventually get deleted. And so that's the basic operation of data loading. All right? In the current system, we have measured speeds in the order of 1.2 terabytes per hour when you have a single data rack of 10 nodes, and that tends to address most of the scenarios that we have found. Some other important functionality of the system includes backup restore. So backup restore is performed in parallel. You know, every single compute node has a SQL Server database. And so when we want to back up the data, we emit backup operations to each one in parallel to each one of the compute nodes. These backup operations then start sending data to the backup restore node, and then we basically catalog all the database backups that we have collected into a folder, right? And that's what it is. The restore operation just basically takes a folder for a particular database, navigates every single one of the backups that exist in that folder, and emits a parallel restore operation to each one of the compute nodes. Fault tolerance, all the hardware and software components have redundancy. So there is dual storage, there is dual compute nodes, dual control nodes, all the networks have dual switches, and so the system is fault tolerant. It's not highly available in the high availability sense because we tolerate one fault and maybe the second one in degraded mode, but then if you go beyond more, the system then needs to be taken care of. There is a system substrate which basically takes care of the setup of the system. You know, we take an appliance from bare metal and apply all the installs of the Windows, SQL Server, all the software installed in the machine, and deliver a working system. When we need to patch or upgrade the software in the computer, there are workflows in the system that take care of that. If a node needs to be replaced, there is a workflow that decides how to take the node offline, keep the machine running, and then enable the service person to come, replace the hardware, and then bring it back to the system. There is an appliance validator. Again, when you imagine that you are servicing a system like this and somebody calls you and say, my query is slow, where do you start? Is it a hardware problem? Is it a software problem? So in order to at least triage whether it's a hardware or software problem, we have a validator tool that crawls, basically it's a collection of agents that crawls across the entire appliance and determines if all the hardware pieces are functioning properly. If everything is functioning properly, then you say, okay, well now let's look at the query. What's the plan? Does the plan look reasonable? And then you kind of move forward. If the hardware is not functioning properly, then there is no point in going further and trying to to figure out if the query execution plan makes sense. Because when a disk is just not working, then you're going to have a big skew in the query execution costs that you're seeing, and so there is no point in trying to debug that query further until you fix the hardware problem. And then we have all kinds of connectivity to standard ETL and BI tools, from Microsoft Stack to third-party connectors like SAS, Business Objects, Informatica, including Hadoop. We have connectors to Scoop, the SQL Hadoop connectivity tool.
So does Hadoop run on the same cluster, or this is a Hadoop running?
No, this is an area that we have right now. I'm going to talk about further connectivity with Hadoop, but right now, the scenario that we handle is one where you have Hadoop running on Linux in some cluster, and then you have PDW running on Windows. Even just that transition from Linux to Windows has interesting implications, engineering implications from the point of view of security. How do you make sure that the data that moves and the security certificates are correct, blah, 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 blah. So we decided to standardize on a Scoop, which is what most people are asking for. And so we provided that. But we have a Hadoop version running on Windows, right? And we are trying to integrate more and more Hadoop into the Windows environment. So in terms of features, SQL 2012, which shipped early this year, has column store. And so if you, I don't know, how many of you have played with SQL 2012? Any of you? No? No one? Wow. So SQL 2012 has column store technology, right? Queries run really, really, really fast. You can experience speedos from 10x to 100x if you're lucky in certain scenarios. It has nice compression. Again, compression is a tricky thing to measure because it's all data dependent, but in some cases you can see 3x, 4x compression. And what we are doing in the next generation of PDW is to basically incorporate the column store technology as part of PDW, right? Single node query optimizations. What happens is data warehousing queries are funny in that a customer may say, give me the top 10 customers on this particular segment of my business, right? You get the first 10, and now you want to drill down into the next one, into each one of those. And so it's like a single customer query lookup that looks like an OLTP query that follows on. And all the data about that customer is in one compute node. So rather than having the entire distributed machinery executing on behalf of a query where all the data resides in a particular compute node, we need a fast path way to go and extract the results from that compute node. So that's one of the extensions we have. SQL Server in its SMP system is a very rich, feature-rich product. It has XML support, CLR support, all kinds of data types. And so PDW focus only on the subset of T-SQL that makes sense for a data warehousing customer, right? But there's always outlier customers who build the first iteration of their application on an SMP system, and I want that one feature that they use in SMP to work in the distributed system. So we are constantly trying to broaden the set of capabilities supported in PDW. Increased data load. If you look at it, all the data comes to the landing zone. You say, well, isn't that a bottleneck? And yes, it's a bottleneck to just go through a single node. Wouldn't it be better to be able to load directly through all the compute nodes? And so we're looking at strategies for doing that. And then finally, Hadoop integration. And so for this, there are different scenarios for Hadoop integration. The first one is the one that I described, where on one hand you have the relational database system sitting on Windows, you have HDFS sitting somewhere in Linux. And there are tools to import and export via Scoop. And that's a scenario that we support today. Then there are other, and you can issue queries on each side of the world that you happen to be in. If you are If your center of operation is on HDFS, you issue MapReduce queries on the Hadoop system, and that's how you solve your task. If you are in a relational database, well, you issue SQL queries and you get your results, right? So the worlds are fairly separate, but there are breaches between the two. Another world is represented by Hadap. That's one of the startups in the industry right now. What they did is they said, well, what if we put the MapReduce machinery for data movement and coordination across the cluster, and then allow queries to span both worlds, right? And that's one of the scenarios that are being built. And then there is another scenario where you have a parallel database system like PEW spanning the world of Hadoop and HDFS, and now you want to execute queries where the data is collocated between the two. And so that's a valid scenario, and we're working on the 3 of them. All right? So, summary, we talk about the PEW fundamentals, what PEW is as a scale-out, shared nothing MPP system. I walk you through some of the core functionality, including the metadata shell database compilation part of PEW, walk you through a distributed query processing scenario, talked about data movement and bulk loading, and discuss some of the features that we are exploring for extensions to PEW. And I'm open for questions. Any questions?
Actually, do you have some application in which you apply Hadoop technology?
What kind of applications do we have for Hadoop? The scenarios that we have, the scenarios that came to us initially were people who, by other reasons, were exploring kicking the tires of Hadoop in their organizations. Okay, so they had Hadoop, hoping that Hadoop will help them solve the scenario of, some collection of clickstream logs or some collection of data, because they had some sort of a web property and they needed to collect all that data. And then they were also exploring acquiring PEW to handle the large-scale data warehousing. And so the first approach, the first scenario that they were interested in was breaching the two. So that's why we went ahead and tried to provide scoop connectivity tools between data warehouse, between Hadoop and parallel data warehouse. And so basically ETL scenarios were the initial set of scenarios that came to us. And we reacted to that by providing those connectivity tools. But now that we have a Hadoop running on Windows, there's a whole bunch of other scenarios that become interesting, right? Like we can have Hadoop running on PEW. I mean, after all, PEW is a cluster of computers, right? You can install Hadoop in there, and then you can say, well, I mean, you want to run a MapReduce task on that cluster? Go ahead. You want to run a query against your tables? Go ahead. I think that the side-by-side nature of Hadoop and SQL makes sense. And then as time evolves, cross-breach scenarios between the two will become interesting, depending on how the technology evolves. Good question. Some other question? No? Oh, another one?
I don't understand what is the device which ensures data integrity.
The device that ensures
In your architecture, what is the device which ensures data integrity?
Data integrity in what sense? Transactional integrity or correctness of the data or?
I'm thinking, how do you ensure some nodes don't on the right the data tables how did you ensure some nodes don't change the indices and
Okay.
the tables?
Okay, so basically data integrity of the distributed system. So all operations run on distributed transactions. So we have a distributed transaction capability. And in the case of indices, if you have an index on a table, the index is not like there is a global index spanning all the compute nodes. Every partition has its own index. So as you are entering data, right, into each compute node, if you declare the index to be unique, then the uniqueness is going to be enforced right there on every compute node. Right? So
Just to clarify, so you use two-phase commit at the end of each of the block matches?
yes, we use two-phase commit. We have the DTC, the Distributed Transaction Coordinator system of Windows. Yeah. At this scale, it works. When you start dealing with thousands of nodes, people question the value of DTC. And so for that, there are other mechanisms. People tend to use workflow engines to be able to manage the staging of operations across multiple, thousands of nodes. All right? No more questions? Thank you.